All right, let's just jump right in here. We are doing a review of the SPICE models that I have here for the diode rectifiers. Earlier, I posted a video having to do with diode rectifiers, which is a critical agent for our power supply. So if you're not privy to what a rectifier is, that's basically AC/DC, right? AC/DC conversion. We use rectifiers, which basically a rectifier is basically nomenclature for a diode that's used to change AC to DC. So in heat of us designing our own lab power supply, I thought it would behoove us to go through the materials and designs on how to do so. So earlier I did a review of Stan Gibilisco's section in the Teaching Yourself Electronics book, which, as I said before, we're going to use probably all throughout this video series. Here I have a manifest of the schematics that represent the basic forms of a diode rectifier that we saw in the video and we saw in the book. I have this on LTspice. Again, as I said in my last video, LTspice is a circuit simulator. If you're unfamiliar with it, we'll talk about it more and more. It's probably my favorite circuit simulator, and we'll get into it more if you haven't used it. It's very useful. It's something that you guys, I know it's like, oh, another thing to learn, but this is very helpful, and it's a great way to start learning electronics and building your circuits. Because what we'll do here is we can dial down the circuits before we build them, and we'll get real world results once we built it, and it'll replicate the circuit basically to the T. So let's talk about this. So right here, as I said earlier, I have all three different rectifiers. So we have a half wave rectifier, a full wave rectifier, and a full wave bridge rectifier. Okay, now I'm going to talk about the circuitry a little bit and show you what's going on and show you, the kinds of things you have to do in LTspice to be able to simulate some of this kind of stuff. And then what we're really going to do, the bread and butter, the meat and potatoes of this whole thing that I'm showing you, this whole video here today, is going to be about analyzing the waveform and understanding the difference in the waveforms that you get out of these different rectifiers. As I talked about in the video, we annotated and we made kind of the rules of thumb about these amplifiers, or about these regulators, or not regulators, I'm sorry, rectifiers. The rules of thumb about these rectifiers, and that's going to be reflected in the waveform. So I'll talk about that as we pull up the waveforms. So what you see here on the left-hand side are just signal generators. Okay. So this is how, in LTspice, this is how you would simulate a, let's see. This is how you would simulate right here is how you would simulate, all right here and right here and right here is how you would simulate an AC circuit, or an AC, just AC signal. So I have an AC signal. Well, you see here where it says sine, so it's a sine wave that's coming out, and it's coming out at 20 volts and 60 hertz, or 120 volts, 120 volts at 60 hertz. All of them are set the same. Why do we have it set like that? Because, of course, in North America, that's what we get out of our walls, so that's what we're used to using for as far as AC. Okay? Now I have it going into, this is actually just an inductor. In LTspice doesn't have transformers. You build transformers off of inductors. So I have an inductor here on the primary side. They're all the same. I have a nominal inductance for it, which is 100 millihenries. So I have 100 millihenries on each of these. Okay. And there is actually, this is a little bit more specific to the program, but this actually also has 1 ohm of resistance just to make the circuit work. It has to have a nominal amount of resistance to make this work. So it's not shown on the screen. It's something that you'd have to tap the, if you tap L2 or L4 or L7 or any of these, and you open up the parameters for the device or the component, it'll show you all the inputs you have to put in there and the parameters, and one of them is the series resistance. So inductors typically have a series resistance. They're measured in henries, but they also have a series resistance. And I just have 1 ohm there. Again, that's not particular. This is kind of, and this is something I wanted to cover as well. You know, this is like a test bed circuit. This is just showing us kind of the bare bones, what we would experience, just a general circuit. This is not something that I intend to build. I just made a nominal model to represent what I want to show you guys. So after this inductor, if you see here, we have another inductor. That's the secondary side of the transformer. Now, these have to be linked. If you see this, it says K, L1, L2, 1. That's basically transformer 1. What that's telling the system, that's a directive that you put a spice directive in there. That's telling the system that these two, inductor 1 and 2, are linked, okay? So those are linked, and that's how you get it to operate as a transformer, okay? So you're going to see when we pull up the oscilloscope, basically, this, what's called a simulation. It's basically, it's like an inbuilt oscilloscope. Here's what it is. So instead of me, you know, piecing this together on a breadboard or something and doing it in the lab, I can just do it here with you, and we run the simulation, which is basically just going to show you, you know, a signal readout. So that's the transformer. That's how we get the transformer. Then we have a diode, and we have basically a dummy load. A dummy load is basically just a resistor that you use just so you can tell the circuit where the energy is going, essentially, just to get current to flow. And again, in the program you need this, and in real life you need this oftentimes. Sometimes you don't use this resistor for actual resistance, not to attenuate voltage or anything like that. You use it sometimes as what's called a load resistor, just so you can have somewhere either to dissipate voltage, or you can have something to tell where the current needs to go. Okay, so that's the basics of this circuit here. And as you can see, as we get further along, it gets a little bit more complicated, and then it gets a little bit more complicated when we go to the full wave rectifier. I'm going to start now just with the half wave rectifier. So the way this works here is that you'd have to go up top and you press simulation, you press run, and then we have our screen with our readout for the oscilloscope. So first I'm going to read just the signal that's coming on the AC. Now you can see that's as pure as you'd want. That's hopefully what we would see coming out of our wall socket. You want to see 120 volts going up, 120 volts going down. So we have a true 120 volt AC swing here. Now, if we go on the secondary side, we'll see it should be the same thing. As you can see, both of those traces, see, this is a nice thing about LTspice. Most simulators, you can do this as well, where they'll let you trace at least 2 signals at a time. So you can, and they'll overlay it and put it in a different color. So the green signal is the input. You can see VN001, that's going to be the input. And then the output, the secondary, is 002 over here, and that's in blue. As you can see, they're almost perfectly aligned with each other. And that's showing you that our transformer is basically 1-to-1, and that's what I wanted. I wasn't trying to step up or step down this voltage. I just wanted 1-to-1, just to give it an example of this circuit here. So you could look at this first circuit with the half-wave transformer as an isolation transformer, okay? So, but what happens here, if we see the first, but then what if I click that and go on the output on the opposite side of the diode, okay? That's what we have on the other side of the diode, is that exactly what we would want? Well, I think it is, and we can also check, we can cross-reference Stan's book and look at the diagram for, where is it? Look at the diagram for half-wave rectifiers, and we'll see that it's basically a mirror image. Okay, so that was this half-wave rectifier. As you can see, the representation here where it skips a cycle, and we can see that it skips a cycle here. So it has a positive cycle, and then on what would be the negative cycle, there's nothing there. It skips a cycle, then you have a positive cycle, and then it skips a cycle, and so on and so forth. And that's why it's called a half-wave rectifier, because you only get half of the wave out of it. It nulls out the negative side, and it only takes the positive side. Because of that, you only have half the wave. Okay? Now again, I can overlay this waveform with the input, and we can see a more clear image of what's happening here. So again, you see the blue and green are almost perfectly overlaid on the positive crest, right? But you see there is a flat line here on the output, which is the blue, after the positive cycle, and that on the negative cycle, it goes completely flat, right? So you basically lose all of this voltage, all this power is what you lose when you use a half-wave rectifier. And we talked about that earlier. What does that do? What's the consequence of that? And it can't pull as much current, okay? So it's going to be deficient in pulling current because of this, right? But we also said earlier that, is that always a disadvantage? Not necessarily, because if we have something that is not going to pull that much current, if it's something in the milliamps range, it doesn't really matter, right? And it can be useful because they're actually cheap to produce. Or you can tap something else. You can tap another winding on a transformer to use with a half-wave rectification if you're using something that's going to take a nominal amount of current. So it can be a very useful thing to do. Because as you can see, the circuitry is simple, and because the circuitry is simple, the cost is also less. So that is your half-wave rectifier, and Stan alluded to this earlier in that book. If I can zoom in here, I don't know if I can't. There we go. If I zoom in here, this is the top crest of the positive cycle. As you can see, the blue line, which is our output, is just below. If we look at the scale here, it's outputting. This goes almost all the way up. We can actually put a line on it. If I want to, I can put a line on it and see exactly where it is. Okay, so at its peak, you're looking at 119.97 volts, 119.97 volts, okay? So we can just round that to 120, right? But if we look at the crest of the output, we only get 115.47, okay? So we're losing about 4 volts there, okay? So we're losing about 4 volts on our output, and again, Stan alluded to that as well, that you lose a little bit of power too with your half-wave rectifier, and there you go. You can see it represented actually in real time on this. Of course, these things are negligible, and you have to remember the caveat to this, which is Stan didn't mention this, but I thought that he should have, is that yes, that is the case, but we also have to remember that this circuit that he showed you in the book and the circuit I'm showing you now doesn't have any filtering capacitors on it. The filtering capacitors are usually going to up your voltage significantly, up to like 15 to 30 volts. It could increase your voltage. So even in your designs, you have to anticipate that. So even though while we're showing you it's not a theoretical, it is true that it does that. But in the real world, you would have a filtering capacitor there, and that would basically null out the lapse in the voltage. That would null out the voltage drop because you would have a capacitor on there that would likely exceed the amount of voltage that you were desiring in the first place, right? So if we had a capacitor on this, we could very well get 126, 100, maybe 130, you know, probably 130 would be pushing it, but something like 126 or something, even with load on it. Once we have a load on it, 123 volts, something like that. Okay, so this is, while it is true that there is a drop, it shouldn't really affect the performance of your circuit in the long run. So that's your half-wave rectifier. Now let's go to the full wave. The full wave, of course, if we see the output or the input of the full wave, is the same thing that we had here. If I overlay that, the same thing. It's just a 120 volt circuit. But what happens here when I go on the output? Now you can see this wave looks a little bit different, and in a second I'll overlay the half-wave rectifier so you can see the difference. We see that there's more cycles here, that we actually have our true cycles. So we're getting a pulse basically for every cycle. It's not skipping any of the cycles. Now the cycles do look a little bit uneven. We can tell that, but again, this is not performance based. Remember, we're just doing this as representation. So, but if in the real world, if we were designing this, we'd want all these crests to be even, and basically, I mean, and eventually we'd want to smooth all this out, right? So that we just have a smooth line here of DC at 120 laying up here. So we would get rid of the crest in general, but we wouldn't have all this what we call like a ripple, okay? So we can see that we have now both cycles represented on the positive side, of the waveform. And why do I say it's represented on the positive side of the waveform? Well, look at this. If I put the input back in here, what do we see? We see that this starts on the positive swing, so it starts on the positive swing, goes up to 120, and they're both almost pretty much aligned with each other. But what happens on the negative swing? You see, this is the input voltage that hasn't been rectified. After it's been rectified, that input voltage that's on the negative swing actually gets mirrored. It gets flipped over to the positive side. That is the effect of having your center tapped transformer, okay? That is why the full wave rectifier is called a full wave rectifier. It takes a full wave, but it does that by basically flipping the negative end and flipping it over to the positive end, okay? So it takes the negative end and flips it over to the positive end. And we can see that represented, I believe, here, maybe. Or we can see it, yeah, we can see it here after. Okay, before the rectification. Before the rectification, let me zoom in a little bit here so you see where I'm pointing at. So this is the positive cycle. This is the positive end here. I'll even get my pointer out here. So this is the positive end of your full wave rectifier right here. And that's what we're seeing here. You see the upswing is positive. The first swing is going to dictate if it's positive or negative. So if the first swing is going upward to 120, then that means it's positive 120. But now if I tap the other side of the center tap transformer, this center tap transformer is basically you can look at it as two transformers, or in this case, it's two inductors that are put together, and the center is tapped and shunted to ground, is put to ground, okay? If I click on that other side, what do we see? We see that it starts on a negative swing, right? So these are basically, it's out of phase is what we call that, right? So they're 180 degrees out of phase, okay? So that means one is negative, one is positive. If we put them both simultaneously, they look like a mirror image of each other, they're just inverted, okay? So they're 180 degrees out of phase. And this is how you get that kind of spiraling look, okay? 180 degrees out of phase, these signals are. And that's truly what happens until you put these diodes in there and rectify it, and then connect the diodes at one end, and then we get our DC output, our full wave DC output that's taking that green, you see that green cycle, it's taking that and it's pushing it up to the positive cycle. So that green negative cycle is pushing up to the positive cycle. And if we can just see that alone again, you see it like that. And again, if I look at the input, that's what that looks like right there. So it's taking that, and it's putting it up to the positive cycle. Now, what is our full wave rectifier good for? Well, we can pull more current with it. It's going to be more consistent. So those are things to keep in mind. Full wave rectifiers typically are going to be probably, I would say, the second to the most used. Bridge rectifiers are probably used more. It all depends, but we'll see why in a second, and we'll just jump right into that. Again, the same kind of concept, same thing that we had going on in the last one. We have our input, and then we have our inductors. This is also using 2 inductors, so this is basically the same transformer, just without the center tap. You see, there's no center tap here because you don't use the center tap with a bridge rectifier. It would null out the purpose of it. So with the bridge rectifier, it has a configuration like this, where you have 2 diodes in series, and then you put the AC line in between the 2 diodes, and then you have a negative tail on the left side and a positive tail on the right side, and your right side on the positive is where you would take your voltage, okay? Now there's one thing in particular that we're going to notice here about the full wave bridge rectifier, and this is why I said it's used a lot. It's used when you want to get the most power out of your transformer. When you don't want to get the most power, or if you want to get only half the amount of power from your transformer, you use a full wave rectifier. Now this would be kind of confusing, because you would say, if I wanted half the power, why don't I use a half-wave rectifier? Well, a half-wave rectifier isn't actually half the power, it's just half the cycle, which is actually just going to give you less current. But your full wave rectifier will give you, if it's just a 1-to-1 and it has 120 volts going in, it'll get you 120 volts out. Okay? But with your full wave bridge rectifier, if we look at this for a second, full wave bridge rectifier, this is the output, or this is the input, 120. If we go on the output, what do we notice? It looks very similar to our full wave rectifier, but do we notice something? If the full wave rectifier is in the blue, and the bridge rectifier is in the green. The signals look pretty much the same, except for what? The size of them, right? The output of the bridge rectifier is significantly larger, right? And you say, well, why is that? Because the bridge rectifier essentially doubles the amount of voltage that you have here, okay? So it'll essentially double the voltage that you have. This is one thing to keep in mind when you're using a center tap transformer and you put a bridge rectifier on it. That will dictate. It's not sometimes it's not the transformer, the rating of the transformer that dictate how much power you can get out of it. It's also the way you're going to rectify it on the opposite end. So let's say if I had like a 600 volt center tapped, if I had like 600 volt center tapped transformer, and I wanted to only use 300 volts of it, what I could do is use, no, let's make it a little bit simpler. Let's say if I had a 300 volt, if I had a 300 volt transformer, center tap transformer, and I only wanted to use that 300 volts, only wanted to have 300 volts out of it, then I would use a full wave rectifier, and that would give me the ability to pull the maximum amount of current out of it, but I would essentially only be using 300 volts. Because remember, when we have a center tap, what this means is I can type this for you guys here. So to illustrate this example, what this means is we have 300 volts on one side, and then we'll have 300 volts on the other side. They're like two independent windings. And in the middle, we have 0, which is the center tap, okay? Now in this illustration, we really have 120 on one side, 120 on the other side, and then 0 in the middle. Okay, but just follow me. With my example with the 300 volts. If we have the 300 volts, then if I just wanted that 300 volts out of that center tap transformer, then I would just use a full wave rectifier, because it's only using one of these sides at one time, and the other time, when it's using the negative side, it's just flipping it over to the positive side, but you still have 300 volts. With the full wave bridge rectifier, if I took the same, that same transformer and had 300 volts on one side, 300 volts on the next side, and I wasn't using the center tap, so there was no 0. I'll just leave the 0 out. The center tap is not there. That is going to effectively give me 600 volts off the output, okay? So this is something to keep in mind and something to keep note of, is that your full wave bridge rectifier is essentially going to give you double the output when you're not using a center tap, because you're basically using the whole winding at once, okay? Because there's no reference to ground in the middle of it, it's not split. In the full wave rectifier with the center tap, this transformer is basically split and it's only being used one half at a time. Here on the full wave bridge rectifier, you don't use a center tap, therefore you use the whole winding. So that's what you want to pay attention to when you say, oh, what do I want to use a full wave bridge rectifier? Well, you want to use a full wave bridge rectifier when you want to use the entire winding of a transformer, okay? When that the voltage allotted to you with that transformer, you want to use the whole thing within that transformer. And that's why you would use something like this, okay? So again, this kind of gives us a good basis for understanding what we would use, why we would use these things and when. Again, with these, the most important thing to do is to pay attention to your voltage conversion, just like I stated here. So when we're building something, when we go further into building our power supply, what's one of the first things we're going to have to figure out then, if this is the case? Before we figure out what kind of rectifier we want to use, we have to actually figure out what transformer we're going to have, right? Because that'll dictate what kind of rectifier we're going to use. If we're going to use a transformer with a center tap or without a center tap, that'll dictate what kind of rectifier we want to use. I'll say a little more about this too. You'll start to understand this better when you get on the market and actually look at components. This is why some of this is important, why I want to talk to you about this, because what will happen is you'll see sometimes you won't find certain sizes of transformers, and you'll say, well, how do I get that voltage? How do I get that voltage? How come I know that things are designed with 300 volts, but I don't find any 300 volt transformers? Because they're not using a 300 volt transformer. They're using a 600 volt transformer that's center tapped. Okay, you follow me? So that's one of the things you have to understand about this, right? So maybe if you want a 12 volt, you want a 12 volt circuit, but you can only find a 24 volt transformer. You use a 24 volt transformer, and you can use it when it's center tapped, and you can get your 12 volts. Okay, you can get your 12 volts that way, or you can just use half of it. That's another thing you can do. Maybe I won't go. This video is not going on too long, so I guess I can make a quick representation for what you could do with for what we could do. There's different configurations here. So what we could do if we wanted to split a circuit in half, let's say. So if we took a circuit like this, what we could do is, instead of using the center tap, just going directly to ground, we could have basically a half wave rectifier on this side, and then we could have a half wave rectifier on the other side. Now, again, this would be something that you might want to do if you had two different voltages that you wanted to make out of this. And then, of course, you would have some kind of like capacitor here that would then go to ground. Electrolytic capacitor. I'm just grabbing quick components here. But you could have an electrolytic capacitor here. And then I'll even cut this out. This will be more true to the design. And you could have another electrolytic capacitor here. Okay. And then you could ground this. And now you effectively have two different windings. You get two different voltages. You could make two different, you can basically get two supplies, like a dual power supply, you know. So out of one transformer, you can get two supplies out of it, doing it that way, okay? So that just gives you kind of an idea of different things we could do. All these things have to be decided, though, basically depending on what's on the market. Again, we're kind of getting into that whole thing too. Like again, like I said in my previous video, a lot of the stuff to figure out in electrical engineering or engineering in general is not just the circuits, it's also supplies. You can only produce what you can find on the market, or you'd have to design it yourself. Typically, on our end of that, we don't have the ability to do that most of the time. Or we don't want to go to the trouble of doing that is usually what it is, you know, because whatever we're doing is not that specialized enough for us to really care that much about having something uniquely manufactured for it. So we have to play with what's on the market, and the market has designed things in a certain way to make them amiable for different projects. But because of that, you're going to find that, you know, there are some things that you won't find straight out. Like I said, certain voltages of transformers and things of that nature, and you'll have to know stuff like this to understand how to actually achieve what you want to achieve. You know, again, let's say if I wanted a 6-volt output and I can only find 12-volt transformers, and I'm like, well, how do I get 6 volts when I have to use things like big resistors? What if I have to what if I want 6 volts but I want it at like 10 amps? That means I have to use like a huge resistor. Sometimes it'd be impossible really and then you'd be just wasting energy. You don't want to put all that energy into a resistor. You say, oh, well, I'll just put a resistor there and it'll you know, bring down my voltage. But then, you know, that thing is going to be burning. You know, you're going to dissipate a lot of. It's just inefficient to do it that way, right? So what would you do before you would think about doing it with a resistor? You would do it actually on your rectification end, which is using half the winding and stuff like that, right? So this is why this stuff is important. We'll talk about this more and more, but I just wanted to give you guys an understanding of what this is like and how we're going to go forward in building our power supply. Let me know if you have any questions. I hope you enjoyed it. Have a good one.